So this is the review video for test number 2. But before I jump into that video, I want to spend a few minutes looking at the 3 versions of derivative. So hopefully this will be helpful for you. I want you to see it in action, so to speak. So I have given you a function, or I've come up with a function 3x squared minus x, and I've given a value of c at x equals 3. So I'm going to write the derivative in the 3 different formats just so you can see what these 3 forms of derivative look like and how they look different, even though they all represent the same thing. Remember that slope is slope with slope and derivative is instant slope. So if we wanted to find the general derivative, in this case we would not consider the at x equal to 3. We would begin with our slope generator, and the general derivative is f of x plus delta x, and a lot of times you'll see that the delta x you will use h instead of delta x, so don't let that throw you off. So that's change in y over change in x, delta x, and again this could be, let me get my pen here, it could be h approaching 0 over h instead of the delta x. Sometimes that's a very often used variable. So when I use this specific function, what I want you to see here in this general form, let me get my red pen, grab the pen, grab that. All right, so the function is 3x squared minus x. So right here I have the 3, and then I'm going to take the x out, and I'm going to replace it with x plus delta x, and I'm going to square it. That comes out of the function, and then minus x, and so I'm taking the x out and putting in x plus delta x. So all of this part right here, that is the y number 2. And notice that it's in general form because I'm using the variable of x. And this is minus f of x minus the actual function. This is y number 1. And delta x encompasses, which it literally means change in x, so it would be x number 2 minus x number 1. All right, so that's what, I'm going to clear these annotations because it kind of gets busy here. Oops, edit, undo. I didn't want to do that. Edit, undo. So let's do this instead. Get rid of some of the writing that I've done. So that's what the general form of the derivative looks like. I'll move this back down in a second. When you see it in the first format of the derivative. So really focus your eyes and your attention right here. The question would be on an assessment, if I had to analyze what the meaning of this expression is, would I A, recognize it as a derivative? Would I know it's the general derivative? And would I know what this is the derivative representing the derivative of? Now, one form of the point-specific derivative, again, notice looks very much like the general derivative. The difference is now instead of having the x value, I have a specific number. So in this format, this would be the number, and in this case, for our problem, this is our c value. And in this, so that's y number 2. Y number 1 is the function value at c. In this case, it's going to be the function value at 3. And it looks very similar to the general derivative, but now we're going to find this is going to calculate the specific derivative at x equal to 3 on 3x squared minus x, whereas the general derivative will create that slope generator, that formula that creates slope for me. So compare what you see here to what you see on the left-hand side, and you'll notice they look very similar. Where they differ is right back here in the y number 2, instead of having the actual function, we have the function value. So we're substituting 3 into f of x. And so this represents the point-specific derivative of 3x squared minus x evaluated at x equal to 3. So we have the general derivative on the left, the point-specific derivative on the right. Then we have an alternate form of the point-specific derivative, and that looks like this. So it's still a y number 2, except for this time it's the actual function minus the function y value. Actual function minus the function y value. over the literal change in x, so it's x minus c, so we have a specific c value. So these two on the right-hand side are both, so this format, get a pen, let's get purple, this is a form of a point-specific derivative, and this is a different form of a point-specific derivative. Make sure that you understand both of those are point-specific. One of them has the entire denominator going to 0, the delta x going to 0, and the other one in this case has x approaching c, because if x approaches c, then the denominator goes to 0, and that's that whole idea of going from that secant line to the tangent line. All right, so then when I take the actual function, 3x squared minus x, minus the y value when I substitute 3 over x minus 3. So really take a look and analyze and think about and study those various forms. And again, really the question for you is, if I were to see the various formats, so again, let me highlight this time in yellow. If I were to see this expression and this expression right here, and this expression right here, the question is this: would I know that I'm looking at a derivative A? Would I know if it's general or point specific? If it's point specific, would I know the value of x that I'm finding the derivative at? So that's what you really want to be able to say yes to in order to be ready for this part of your assessment. So for test number 2, the bullet items, the things that you need to know and to be able to do, are listed in your packet, and you really need to take the time to go through each of these and analyze yourself. So for example, and change these into questions, am I able to find the derivative using the power rule? Don't forget about rewriting with algebra. So when I read this, I really felt good about myself. But when it said, don't forget about rewriting with algebra, I became a more of, I probably need to practice some rewriting in algebra. And you can use whatever scale you want to, happy face, frowny face, flat face, or you can do a 5, 4, 3, 2, 1. But I think this is an important time to analyze yourself and determine what you know and don't know. So then in the second bullet, I would say, do I know the derivative of sine x, e to the x? And the way I would figure that out is I would say them. The derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of e to the x is e to the x. And so I would say, well, I feel pretty good about that. So do that for each of these items. Also, take the time to determine if you have a question about what the bullet's saying, so you can ask me about that. So I'm not going to continue reading that, but I am going to jump into the problems that we're going to do to help prepare and review for this test. Focus on how I read, focus on the things that I underline that help me to unpack the problem. Given a function, and so here's my function, it happens to be quadratic, so it would be graphically a parabola. My job, number 1, or I think I only have one job, is to write the equation of a tangent line. So as soon as I realize in number 1 that I'm writing the equation of a tangent line, I'm going to stop and write down my model. This is sort of my target. This is what my answer should look like. That's the format that it's going to take. So I want my line to be tangent to the parabola, and I'm thinking back over here, I see that parabola with a positive a value, so I have a parabola opening upwards. And I want a line tangent to that graph. So I don't know where the line's going to be, but my line that I'm going to create is also perpendicular to a given line, 2x plus 10y equal to 7. All right, so I got to figure out what is the importance of telling me that the desired line, so right down here, this is my desired line. My desired line is perpendicular to 2x plus 10y equal to 7. Well, I have to remember the fact from my Algebra 1 days is that perpendicular lines have opposite and reciprocal slopes. Opposite and reciprocal, meaning I'm going to change the sign and I'm going to flip the fraction. So then I have to figure out the slope of the given line. That's all I care about in this line over here. So to find the slope of the given line, I'm going to get y by itself, so I'm going to subtract 2x from both sides. So there's my 2x on the right-hand side. And then I'm going to divide everything on both sides by 10. So I get negative 2 over 10 times x plus 7 over 10. I don't really care about that because remember I want the slope. And I can see that the slope of this line is negative 1/5. That is the slope of the line that my line is to be perpendicular to. And since perpendicular lines have opposite reciprocal slopes, that means that the slope of my line is going to be the opposite reciprocal of negative 1/5. So the slope of my line is 5. And at that point, that's really all I care about. And don't cross stuff out like this on your paper. But that's really all I care about with that additional line. I was able to get the slope of my particular line. All right, now the next thing that they tell me is that my line, or the next thing I realize that I'm going to need is an x and a y value, and they don't give me an x or a y value. So I've got to ask myself, how am I going to get the x and the y value? Well, I have a little bit of a clue right here. Remember that this was the, let me write it out, this was the slope of a tangent line. Now, slope of a tangent line is derivative. So that means that the derivative of my function, which is f of x, that means f prime of x is equal to 5 somewhere. That's going to give me the value of x. So I'm going to take the derivative of the function, which is 4x minus 3, using the power rule, and set that equal to 5. Add 3 to both sides and get 8. Divide both sides by 4, and x is equal to 2. So now I have the x value for where my line is tangent to the curve. To get the y value, I'm going to substitute 2 into the original function, not the derivative. I already know what the derivative at 2 is. I want the y value. So I'm substituting 2 into the original function. So 2 squared is 4, times 2 is 8, minus 3 times 2 is 6, plus 2. 8 minus 6 is 2, plus 2 is 4. So f of 2 is equal to 4. So now I have all of my elements. I have an x number 1 of 2, I have a y number 1 of 4, and I have a slope of 5. So I'm going to come down here and write the equation of my line. So y minus 4 is equal to the slope of 5 times x minus 2. And I'm going to get y by itself, always as the last step. We always want y by itself when we write the equation of a line. And so this is the equation of a line that is tangent to f of x at x equal to 2. And this line is also perpendicular to the given line. And you can verify or validate all of that by putting this into your graphing calculator and actually seeing that. So that's problem number 1. I'm going to clear the annotations and jump to problem number 2. I think I'm going to. There we go. In problem number 2, we're finding that mysterious value of k that forces the function to be continuous. So my first piece is a parabola, which is normally continuous, and I have a line which is normally continuous. So the only value of x I'm worried about is this breaking value of x equal to 2, so I'm going to substitute 2 into each piece. 2 squared is 4, and 4 times k is 4k, and because of the equal to, that would be a solid point if I were to graph it. I'm going to do the same thing with the x value of 2, my breaking value. I'm going to substitute it into x. 2 times 2 is 4, and 4 plus k is 4 plus k. And then because I do not have an equal to, I have an open circle. So right now, my function is possibly not continuous. So in order to force this function to be continuous, if these x values are 2, then the y value has to be the same. So this y value of 4k needs to equal this y value of 4 plus k. I'm going to subtract k from both sides, and that gives me 3k equal to 4. Divide both sides by 3, and k is equal to 4/3. So if k is equal to 4/3, if I rewrite this equation, I'll actually do that since we have the time in a video. This would be 4/3 x squared and 2x plus 4/3. This piecewise function is guaranteed to be continuous. If k is a different value of x, then the function will not be continuous. Problem number 2. Problem number 3. In number 3, we're going to examine the graph over here to the right of f of x, and we're going to determine all values of x where a, the limit does not exist, so we have 3 things to do here, b, the function is not continuous, and c, where the function is not differentiable, and explain why. Write a complete sentence using appropriate math notation. So I'm going to start over here on the, well, let's go over here near the graph. So 3a, where does the limit not exist? Well, the first place I see the limit not existing is at x equal to 1. So the limit as x approaches -1 of f of x does not exist because the limit, now remember this is back to limits, the limit from the left, so the limit as x approaches -1 from the left hand side of this given function in the graph approaches a y value of 3, which is not equal to the limit as x approaches -1 from the right side, which approaches a y value of a little bit less than 1, I'll call it 0.8 of f of x. This is an estimated 0.8 equal 0.8. And you don't have to declare those y values. You really just have to tell me that the left and right limits do not agree. Now remember, we're talking about limits. We're not talking about derivatives right now. The next place that I see where the limit does not exist is at x equal to 0. I'm not going to write up again why the limit doesn't, because it's the same reason. Technically, actually, no, we need to write that the limit as x approaches 0 from the left side, because that's going up to infinity, does not equal the limit as x approaches 0 from the right side, which is a y value of 3. So we need to do the similar sort of write-up that we had right here to get credit for the second place. So I'm not writing everything up, but I will explain it. In the third place, well, everywhere else the limit does exist. Remember that because the left and the right limits are agreeing with each other at x equal to 1, that the limit does exist, and we were looking for places where the limit does not exist. All right, let's go on to 3b. So I'm going to clear those annotations, and I'm going to go to 3b. And now our lens is different. We're looking at the same graph, but we're looking at it from, get a white pen so we can show. But we're looking at it from a continuity point of view. So I know that in 3b that the function f of x is not continuous at x equal to -1 because up here there is a y value. But we already stated that the limit does not exist, and that's the second reason why a function might not be continuous. So I'm going to say the limit as x approaches -1 of f of x does not exist, and that's all I need to say to justify the continuity. F of x is not continuous at x equal to 0, and in that case I'm going to say the same thing. The limit does not exist, so I'm going to do basically the same write-up. And for the third place where there's a discontinuity, which is right here at x equal to 1, I do see a y value right here, so there's a y value of 2. The limit does exist, but they don't equal each other. So for that case, I'm going to say the limit as x approaches 1 of f of x does not equal to f of 1. Again, I could have quoted the limit value, and I could have quoted the y value to show even more strongly that they do not equal each other. And now let's look at the same problem again from the lens of differentiability. So here we're looking for places where there is no derivative. So I'm going to start at f of x is not differentiable, has no derivative, at x equal to -1 because f of x has a discontinuity at x equal to 1. That's the easiest thing to figure out. If there's a discontinuity, there's no derivative. I'm going to say the same thing for x equal to 0. I'm going to say that f of x is not differentiable at x equal to 0 because f of x has a discontinuity at x equal to 0. I'm going to say the same thing for x equal to 1. There is a discontinuity at x equal to 1, so there's no derivative there. And then the last place that I'm going to consider is up here where I see something that looks very much like sort of absolute value-ish. In other words, the slope on this side is constant and positive, and the slope on the, I should say, the derivative on the left side is constant and positive. The derivative on the right side is constant and negative. They're not moving towards each other. So the two derivatives, the left derivative and the right derivative, do not equal each other. So then my statement is going to be f is not differentiable at x equal to 1 or x equal to 2 because, and this is where we're going to have to write our left derivative statement. The limit as x approaches, we are approaching the x value of 2, and then when we write our statement, we're going to write the function, so f of x is the name of the function, minus the function at 2, change in y. Oops, that's from the left side. Almost missed that. Over x minus 2. So that's literally saying the slope coming from the left side, the instant rate of change, the derivative from the left, does not equal to, and I'm going to write it down here because I'm out of space, the limit as x approaches 2 from the right side of y number 2, the function, y number 1, the function value at 2, over x1 minus x2, or x2 minus x1. And so that's my statement for for x equal to 2. All right, let's come back here and let's do a reset. All right, number 4, we're looking at the same graph again. So we're looking at the same graph again. Is there a guarantee that on the interval from 0.5, so 0.5 is about here, to 2, which is right here. So I have a closed interval. I mean, I can sort of dot that off. I'm just showing that this is the place where I'm looking at the graph from 0.5 to 2. Is there a guarantee that on that interval that there is a value c on this closed interval such that the y value, notice how I read that. I didn't say f of c is 1 because I just have to understand that f of c is saying a generated y value. Reason being, I now know that I have launched into the intermediate value theorem because it's a question about a y value on a closed interval. Using complete sentence and mathematical reasoning, construct an argument to support your position. Well, when I look at the graph from 0.5 to 2, I clearly see a discontinuity here. I see a discontinuity here. Well, that is condition of the intermediate value theorem. So my write-up is going to say something like, the function f of x is not continuous on the closed interval from 0.5 to 2. Therefore, there is no guarantee that f of c is equal to 1. And that's really all I have to state. I don't have to say because of the intermediate value theorem, because it's really not because of the intermediate value theorem. We can't even apply the intermediate value theorem because the condition is not met. So once I declare that the condition is not met, then I can go ahead and say, I can't promise you that there is a y value of 1. Maybe there is. And honestly, if I erase some of these markings, come on, there we go, the eraser. So I'm going to come back in here. All right, so in that region, right here, there is a y value. Well, that's a little bit to the left, but let's see if we have another place. Y value of 1, that's kind of outside of 0.5, so that's not even really in there. Actually, I guess there isn't in this graph, but there could be, but this one actually there is no y value of 1. All right, so let's go on to letter B. We're looking at the same graph. So now we're changing the interval, and this time the interval is going to go from -3, so there's -1, -2, -3 is right here, to -1.5, which is about right here. So we're blocking the graph off here and here. In that region, we can see that this graph is a continuous function, so that's working to our favor. Is there a value c such that f of c is equal to a y value of 2? Use complete sentence and mathematical reasoning to construct an argument. So this time I'm going to begin by saying f of x is continuous on my given closed interval. I have to be specific. Remember, that's something that we've talked about. -3 to -1.5, period. Then I'm going to state the endpoint y values. F of -3 is equal to -1, and f of -1.5 is equal to, I'm going to call it at about, well, it's less than 2, so I'm going to say maybe 1.75, -1.5, maybe. Actually, it looks like it's about 1.5. We're just estimating, and that's okay. Equal to 1.5. All right, now notice 2 is not, the y value of 2 is not between -1 and 1.5. So I'm going to say 2 is not between -1 and 1.5. I did claim that y value correctly, yes. -1.5, 1.5 estimated. Therefore, there is no guarantee that there is a c where f of c is equal to 2. So in both of these cases, we have refuted and cannot make a guarantee that the questionable y value is going to occur. Let's clear the board and let's go on to number 5. So in number 5, we are back to limits. Gotta love those limits. So we are looking at left-end behavior. I can see that we're moving towards negative infinity, so we're looking at left-end behavior. Looks sort of like a rational function, but I see that exponential component down there, so it doesn't behave as a rational function. So I'm going to think of my most favorite very negative number and quote-unquote substitute. So I'm thinking that would give me 4 over 1 minus 10 raised to a very negative number. Now, because the 10 has a negative power, I'm going to use algebra 1, and I'm going to do a rewrite, create a complex fraction. The 1 does not have a negative power, so it's not going to go into a denominator. The 10 is going to go to the denominator, and because I've moved the 10 to the denominator, its power now becomes a positive power. So let's think about that. 10 raised to an infinitely large number. So I have literally, I'm going to divide one piece of bubble gum into an infinite number of parts and then share it with people. If I divide 1 into infinite parts, the value of that fraction is approaching a value of 0. Therefore, 1 divided into infinite parts is approaching a y value of 0. And so I have 40 over 1 minus 0, which means that this function will approach a horizontal asymptote on the left of a y value of 40. Number 6. In number 6, it looks like it sort of wants to be a derivative expression. It looks sort of like I have a y number 2 and a y number 1. So this is making me wonder if I have an f of x minus f of c. So the first thing I'm going to do, I'm guessing that this is the value of c. I'm going to find out if I substitute 5 into 34e to the x. So let's do that. 34e to the 5th power. Is that equal to 40? Of course not. So therefore, even though this looks, it's one of those situations where it's a look-alike. It looks like a derivative, but it's not the real thing because it's not f of x minus f of c. Therefore, instead of being a special limit statement, which is a derivative, it's just a a limit, sorry. Instead of being a limit that's a derivative, it's just a limit. So remember, my strategies are to try direct substitution. So if I substitute 5 into the denominator, I will get 0. So division by 0 is undefined. So the next thing I'm going to do is look for factoring opportunities. Now I see in the numerator that I can factor out a 2. So that would be the limit. Whoops. That would be if I factor out a 2, because I'm hoping that this discontinuity will remove. Let's make that a little bit neater. I can do better than that. And let's make it blue. Let's get a pen. Let's make it blue. So I will have the limit as x approaches 5. If I factor out a 2, that'll give me 17e to the x plus 20. Clearly, that's not dividing out with an x minus 5. So now I'm thinking Algebra 2 pre-cal, which means I now have a non-removable discontinuity. And since I have the x minus 5 factor will not factor out, that means graphically I'm going to have a vertical asymptote at x equal to 5. And if I have a vertical asymptote at x equal to 5, that means the limit is not going to exist because of unbounded behavior. So for number 6, I'm going to say does not exist because of unbounded behavior. But look what I had to do to figure that out. I had to think about that. I had to think about the non-removable discontinuity. I had to think about whether I had a derivative. I had to think about what would appear, a vertical asymptote. All right, let's clear the board and let's go back to number 7. All right, in number 7, the table below indicates the number of points scored. Oh, this is kind of sad. A sad example by the Quince Orchard football team during the 2013-2014 season. Unfortunately, we don't have a season this year. Here is the game number 1, 2, 3, 4, 5, 6, 7, 8, 9, and the points that were scored during the game. Letter A, we're going to determine the average rate of change, which is algebra, A for algebra, algebra 1 slope, from the first to the 5th game. So that's literal, change in y, show me the difference quotient, you know that's important, 52 over 35 over 5 minus 1. And so we can simplify that to be 52 minus 35 is going to be 17 over 5 minus 1 is 4. And then it asks us or tells us to, in a complete sentence, explain whether the number of points is increasing or decreasing over this interval. Justify your answer. So I would say something like over the interval, or nah, let's be more real because this is talking about games. I mean, you could say over the interval. It really doesn't matter. And I think I'm going to type this because I can type faster than I can write and it's less sloppy. So let's bring in my little typing here. Let's see how I do with that. And make that a little bit smaller. Let's make it like 12. All right. So I would say, use the words of the prompt from, let's make it color, let's make it blue. All right. So notice how I'm plagiarizing the words from the first to the 5th game. The number of points, I'm plagiarizing, just reordering the words, scored by the QO football team is increasing at a rate of 17 fourths points points per game. Let's move that out. I'll move it down here. Points per game, because the average rate of change is positive. Right, so it's important to just simply take the, we're plagiarizing the words of the prompt to do the write-up, and you have to have the elements of the interval, you have to have what quantity we're talking about, which is points scored in a game. We have to have the element of increasing or decreasing, we have to have the rate with correct units, and we have to have the y. So that's letter A. Reset, and let's go to letter B. Letter B, grab your pen, there you go, and go. We are approximating the instant rate of change, which is derivative, approximating the derivative at game 4. So game 4 is right here. So we're going to go a data value below and above, and we're going to borrow. It's very important that you write up the 52 minus 7 over 5 minus 3. And that's going to be, make sure that you show the difference quotient, very important for the AP test if it's a show your work problem. And so that's going to be 45 over 2, and that's points per game. Then I need to write up a concise statement that explains or justifies if the points are increasing or decreasing. So I'm going to say, notice this time I'm not doing an interval of time, at the, or I've just used their words, at game 4, the number of points scored by the QO football team is increasing at a rate of 45 over 2, you could make that a decimal, it doesn't really matter, points per game, not squared. It's change in y over change in x. It's the y units over the x units. 45 points per game, because the instant, you could say derivative, but I'm just using their words, instant rate of change is positive. That's what we're looking for as an explanation. Has all the elements at game 4, the quantity being described as points scored. The points scored are increasing, the rate, the units, and y. Number 8, in a complete sentence, explain the meaning of each expression below and then evaluate the expression. So it looks to me like we're looking at some possibly general and point-specific derivatives. So let's see, it looks like right here we have f of x plus h minus f of x over h. So to me, it looks like we're looking at the general, let's type again, I like that better. I should do this more often. Erase. Just do this. Come on, Jernigan, you're smarter than that. Okay. So it looks to me that we're looking like the general derivative of x squared minus x minus 4. That's what this expression is, because that's what they said, explain the meaning. Let's move that up. There we go. And so then evaluate the expression. So I know by the power rule, the derivative of x squared minus x minus 4 is 2x minus 1. So that is my slope generator because it's a general derivative. In letter B, I'm looking at f of x. It looks like minus f of c. So let's check that out. I'm going to substitute 2 in place of the given function. So that would be 2 squared is 4. I just changed colors. 2 squared is 4 minus 2 minus 4. So that would be 4 minus 2 is 2 minus 4 is negative 2. All right, so yeah, that's right, because that would be minus negative 2 is a plus 2. So we have a point specific, I'll write it. We have a point specific derivative, derivative of x squared minus x minus 4 at x equal to 2, and so I know the derivative of x squared minus x minus 4 is 2x minus 1 using the power rule, so that would be the derivative. And f prime at 2 would be 2 times 2 minus 1, which is 4 minus 1, which is 3. All right, number 9, we're getting here close to the end, hopefully, because I have to see period 7 in class in just a few minutes. In number 9, letter A, we're going to need to do a rewrite before we can find the derivative. So 9a is going to become h of x equal to 6x to the 1/2 power plus x 3x to the 1/3 power. So h prime of x using the derivative is half of 6 is 3x, decrease the power by 1, 1/2 minus 1 is negative 1/2, plus a third of 3 is 1, so that's going to be x. 1/3 minus 3/3 is negative 2/3, and you do not have to move your powers up and down and all around. You can leave them right where they are, even though the textbook will probably do something different. These aren't textbook exercises. In a letter B, the function is in power function form. Each term is in power function format, so the derivative using the power rule is 13 times 4 is 52. Decrease the power by 1. The derivative of the constant 5, which is your AP score, is 0. The derivative of the third term, 2/3 of 3 is 2. Decrease the power by 1, so 2/3 minus 3/3 is negative 1/3. The last term, negative 1/2 times negative 6 is 3. Decrease the power by 1. Negative 1/2 minus 1 is negative 3/2. Letter C, that's in power function form, each term, so the derivative is 15x squared for the first term. Second term, half of 4 is 2. Decrease the power by 1, goes to negative 1/2. The derivative of cosine is negative sine, so the negative times a negative makes a positive, and the derivative of e to the x is e to the x. And then letter D, this is classic and famous, ladies and gentlemen. Be prepared to handle this. This is a little bit of 4th grade math. I'm going to first begin by rewriting this expression so that each term has its own denominator of x squared so that I can simplify. This is 3 pi x to the negative 3 over x squared, giving each term its own denominator, x to the 2/3 over x squared plus 2 over x squared. This is really important that you can handle this. Now I'm still rewriting, so I'm going to reduce. When I reduce the powers in the first term, that becomes 8x squared. In the second term, the power of 2 in the denominator goes to the numerator and becomes 3 pi x to the negative 5. In the third term, be really careful. 2/3 in the numerator minus 6/3 becomes negative 4/3, because when the 2 goes to the numerator, it becomes negative, and when we write it as a denominator of 3, we get 6/3, and the last term becomes 2x to the negative 2. So this was 4th grade fractions. This is Algebra 1 exponents. Now I'm going to take the derivative finally. So the derivative of the first term is 16x. The derivative of the second term, negative 15 pi x to the negative 6. Remember, when you decrease a negative, it gets more negative. Derivative of the next term is going to be plus 4/3 x to the negative 7/3. Decrease the power by 1, so negative 4/3 minus 3/3. And then for the last term, we get 4x, decrease the power, negative 3. All right, we're almost there. One more question. Number 10, it says determine the values of the domain where the derivative, see, translate your words, derivative is negative 2. So that literally tells me what to do. Take the derivative of this function and set it equal to 2, negative 2. So the derivative of the first term is 6x squared. Derivative of the second term is 13x using the power rule, and derivative of the third term is negative 7. Set equal to negative 2. So now we have to solve. This is a quadratic equation. Do not add 7 to both. Do not add 7 to both sides. We have to make the quadratic equal to 0. So we're going to add 2 to both sides. So 6x squared minus 13x. Adding 2 makes negative 5 equals 0. All right, I'm going to factor, or I'm going to try to factor. 6x, probably only try, I don't think 6x is going to work. So let's do 2x and 3x and see if that works out for me. I don't do split the middle. I do trial and error, so 2x and 3x. I'm trying to make a 13, and that seems like, so 5 times 3 is 15, so that's looking good. 15 take away 2 is 13. I want the 13 to be negative, so I'm going to do a minus here and a plus here, equals 0. So x is equal to 5 halves, x is equal to negative 1/3, and so on that graph, that's where the derivative would be negative 2.